extreme value theorem. If f is continuous on a closed interval from a to b, then f has both a maximum and a minimum value on the interval. So recall that extreme values are locations where we have maxes and mins. So if we know that f is continuous along a closed interval, then we're guaranteed that the function takes on both a maximum and a minimum value, at least one of each. It could be more than one. So visually, to show an example of this, let's say we have our function f. It's running from a to b. We will have reached a maximum and a minimum along that interval, assuming, this is really important in relation to this, it needs to be continuous and the interval has to be closed. Okay, two very important conditions for this theorem to hold true. So we need to make sure we're considering that when we're evaluating whether or not this function will have a maximum and minimum along a certain interval. It has to be continuous and it has to be closed. So let's look at what would happen if one or both of those things were not met. So in the case where we have to take on a closed interval, if I just open up the interval and the endpoints with that same graph, this function never takes on a maximum or a minimum value from a to b, because in this case, where we would expect the max and min to occur would be at the endpoints. And because those endpoints don't exist as function outputs for this specific interval, it doesn't take on a max or min. So for this extreme value theorem to hold, it would be necessary that we have a closed interval from a to b. Now, where the continuity aspect would become necessary is if I do close the interval, but put discontinuities at the endpoints, this now is closed from a to b. It takes on all values from a to b, including a and b, but it still does not have a maximum or a minimum value. Because of these removable discontinuities, again, I would expect the minimum and maximum to be at the endpoints visually, but because the actual output are in these two locations, those aren't maximum or minimum values along the interval. So those are some counterexamples, or not counterexamples, but examples where if I remove the continuity aspect or remove the closed interval aspect, this theorem does not hold. So two necessary conditions that must be true to guarantee that I will have a maximum and a minimum. Rolle's theorem. If f is continuous at every point on the closed interval a to b, and differentiable at every point on its interior a to b, and f of a equals f of b, then there is at least one point in the interval where the instantaneous rate of change equals 0. Okay, so let's break this theorem down. First of all, we have to have continuity. Second, it's differentiable at every point. So differentiable at every point on the interior, which means visually we're going to have no cusps, corners, or vertical tangents. The other place where differentiability fails is if it's discontinuous, but we're already guaranteeing continuity at the beginning of this theorem. Then the other thing is f of a equals f of b, which means the outputs at the endpoints of the interval are the same. Then we know that we have one point inside of that where the instantaneous rate of change equals 0. And visually, the instantaneous rate of change represents the slope of a tangent line. And if the slope of my tangent line equals 0, I will be able to find a horizontal tangent on this function at some point between a and b. So a horizontal tangent exists. So visually, let's break this down. We got this function from a to b, where f of a equals f of b. Super important to guarantee this. So the outputs, f of a and f of b, are the same. Then, connecting these endpoints, I have to guarantee continuity and differentiability. So I can't have any corners, cusps, or vertical tangents, and I can't have any breaks as I draw a graph or a function from A to B. Oh. So I've taken care of every condition that needs to be met for this theorem to apply. This theorem says that under those three initial conditions, continuity, differentiability, actually I should include closed interval as well. So four conditions: continuity, closed interval, differentiability, and the outputs at the endpoints are the same. I can find a horizontal, oh, I shouldn't say horizontal exists, but rather a horizontal tangent exists at some point C. And we should be able to see that I can draw one. Right there. So there's our point C. Now, why is it necessary for the outputs of the endpoints to be the same to guarantee a horizontal tangent? Well, let's look at an example where they're not the same and see if we can draw a graph where there is no horizontal tangent to show why that is an absolutely necessary condition. So we would want to highlight the importance of this condition as it relates to this specific theorem. So if I draw a graph where the outputs of my endpoints are not the same, there's no guarantee that I will have a horizontal tangent. For example, I could draw something like this. So that is continuous on a closed interval, and it's differentiable at every point, but there is no point where the instantaneous rate of change is zero. Now, I can draw a function that does have an instantaneous rate of change equal to zero, so it is possible to do it, but there's no guarantee. But there is a definite guarantee that I will have an instantaneous rate of change of zero if the outputs of the endpoints are the same. Okay, so that's the condition that makes the instantaneous rate of change guaranteed to be zero at some point. And the way to think of it, in more of layman's terms, is I have a starting point f of a, and I want to get back to that same point as I move along the x-axis. So how do I get back to that same output? Well, I would have to flatten out at some point along my journey to get back to that starting position, assuming I'm maintaining continuity. So if I wanted to draw a line, erase this, and you can try this yourself. If you draw 2 points, they're at the same height, and you want to draw a line between them that represents a function, you have to flatten out at some point to get back to that same height. There has to be points where the curve flattens out. There's no way you can do it otherwise. So that's a good way to think of the Rolle's theorem. Guaranteed to have a horizontal tangent line at some point or an instantaneous rate of change, assuming the outputs of the endpoints are equal. But now, we want to ask ourselves, is there anything that's guaranteed if the endpoints' outputs are not equal? And that brings us to the mean value theorem, where it says if f is continuous at every point on a closed interval and differentiable, and if we remove that condition of f of a equaling f of b, well then we know that there should be at least a point C where the instantaneous rate of change equals the average rate of change. So we're going to be able to guarantee ourselves that instantaneous rate of change will equal the average rate of change, not just that specific value of zero. So the Rolle's theorem is convenient, easy to understand theorem visually, but it's very specific. So when we say average rate of change, we're talking about along the endpoints or between the endpoints of the interval. So removing that condition, we're still guaranteed to know something is true about our instantaneous rate of change. So let's look at a graph to illustrate the point. If, I'll actually put another peak up here. So I draw a function from A to B, and it's clear that the outputs at the endpoints are not the same. It's differentiable at every point still. It says the instantaneous rate of change should equal the average rate of change. So visually, what does that mean? Instantaneous rate of change, we know, is slope of the tangent line. And then visually, what's the average rate of change? Well, that's the slope of the secant line. So if I draw a secant line connecting the endpoints, that will represent the average rate of change, or its slope will represent the average rate of change along the interval from A to B. So what this is saying is, visually, you should be able to draw a tangent line that has the same slope as that secant line. Same slopes would mean you're trying to draw a line that would be parallel to that green line. And there could be more than one location, which is why I drew this specific example. So here's one spot where the instantaneous rate of change would equal the average rate of change. So let's call this point C. That's one location. But there's also another location. I could draw a tangent line up here. So there could be more than one spot where the slope of the tangent line equals the slope of the secant line, or there could be more than one spot where the instantaneous rate of change equals the average rate of change. But there's guaranteed to be at least one location where that is true. Now, from an equation perspective, how can we represent this fact? This is what you're looking out for in the mean value theorem. We want to say the instantaneous rate of change, which is the derivative at some point C, should be equal to the average rate of change across the interval, which is just our change in y over change in x, so the change in the output over the change in the input. So this is the equation that's associated with mean value theorem that you should be familiar with. So those are three theorems that you want to be have a good working knowledge of and be able to understand what they mean.